All right, so we're going to look at this function, and our main goal here is going to be to find the critical points of this function, where the function is increasing, decreasing, and any extreme values of this function. But before we get into all of that, we're going to do a couple things that are really just from the function instead of coming from the first derivative of the function. So even if it doesn't tell you to, in any problem, you should always think about the domain of the function and a little bit about some basic features of the graph of the function. So all of those things come from the original function itself, and then we'll look at all the things we get from the first derivative as well. All right, so when we think about the domain of this function, one thing you should notice is this radical. And so if we're going to have real valued outputs, we need that expression inside the radical to be greater than or equal to 0. So we need 3 minus x to be greater than or equal to 0. So if I solve that for x, if I add x to both sides, I get this expression, which says x is less than or equal to 3. 3 is greater than or equal to x, or x is less than or equal to 3. So our domain is -infinity to 3, if I write that in interval notation. So that will tell us some things about our values that we should expect to get for our critical values, that they need to be in this interval. If I get some answers that are outside that interval, those would be extraneous solutions, and I would discard those. Other things that might be helpful here is to think about some important points on the graph. On any function, important points would be intercepts for the graph. So x-intercepts occur when y equals 0. So I'm going to put 0 in for the output of the function and solve for x. Right, I'm not going to write out all of that algebra here because hopefully you all are OK with algebra. But here I have a product of two things that multiplies to give 0. So either of these two factors could be 0. So I could have x squared being 0, which would give us x equals 0. Or I could have this radical expression being 0, which would occur only when the stuff inside is 0, which would occur only when x equals 3. So I have two x-intercepts on the graph, one at x equals 0 and one at x equals 3. I'm going to do a little sketch of a small graph up here. We'll look at a little bit better graph later. But I know I should have a couple points on the graph at x equals 0 and x equals 3. Another important point might be a y-intercept. To find a y-intercept, that occurs when x is 0. So putting in x equals 0 actually turns out to be the same point we've got here. When I put in x equals 0, x0 squared times the square root of 3 minus 0, I get 0. So y equals 0 is our only y-intercept. And then other things that might be helpful is thinking about end behavior of this graph. So that would be really limits as x approaches the ends of the domain. So as x approaches -infinity and as x approaches 3. Notice that x can really only approach 3 from one side because of our domain restriction here. So those are a couple limits. Those are pretty straightforward limits to think about as x approaches -infinity for this function. So limit as x approaches -infinity of the function. All right, so when I square a large number that's negative, that's going to be very large. So the x squared part will approach infinity. And when I have a large in size but negative number in here, the minus here will turn that into a positive expression inside the radical, and that will also grow large. So all of this will approach infinity. That tells us that on the left end of the graph should be going up. And then the other end of the domain is 3. And we can really only approach 3 from the left because of our domain restriction here. So as x approaches 3 from the left of the function, and we can use a substitution shortcut there to do that. So I'll have 9 times square root of 0, so we'll get 0. So on the right end of the graph, we're approaching this point that's here at 3, 0. All right, so even if it doesn't ask you to do that stuff, that's all stuff from the original function that's helpful in thinking about the stuff it actually does ask you to do, which would be the intervals where the function's increasing, decreasing, finding critical points and classifying them as local maxima, local minima, absolute maxima, absolute minima, or neither. All right, so all of that stuff comes from the original function. All of the other stuff that we're going to find in this video is going to come from the first derivative of the function. So I need to find that first derivative. In order to do that, I want to think about this 3 minus x that's inside the radical as being to a 1/2 power. And then we'll use product rule to find that derivative. At this point, you should be OK with finding those derivatives. So let me write that here. So product rule, the derivative of the first function times the second function plus the first function. And then here's where I'll need to think about the 1/2 power that's there. So times the derivative of that second function. So I'll have times 1/2 times 3 minus x to the negative 1/2. And then times the derivative of what's inside. So I'll end up with a -1 from that derivative of what's inside. That first derivative is a little bit messy there. So before I do too much more with that, I might tidy that up a little bit, especially this second term after the addition. I can make that a negative. And then I have this that I could rewrite as a square root. And because I have a negative exponent, I'll put that on the denominator. So this is just tidying up before we do too much more with this. So minus, because of the -1 here. And then on the numerator, I'll have x squared. And on the denominator, I'll have 2 times square root of 3 minus x. That square root's on the denominator because of the negative fraction exponent there. OK, so there is my first derivative. And in order to find all of that stuff we talked about, critical points, intervals on which the function's increasing, decreasing, and extrema, I need to start by thinking about two things: where that first derivative is 0 and where that first derivative does not exist. So I'm going to start with that first. This first derivative does not exist at places where these things would be undefined here. So we already have a domain restriction, which will take care of this problem here. But we have another issue here because this square root is on the denominator, that x equals 3 is a place where the derivative does not exist. It is in the domain of the function. X equals 3 is in the domain of the function. But because of this denominator in the derivative, x equals 3 would be a place where the derivative does not exist. So that is a critical value of the function that occurs when the derivative does not exist. So I'm really looking at domain related to this derivative here. I already have some domain restrictions here. But the one new restriction I get from the derivative is that this denominator can't be 0. So x equals 3 makes this derivative undefined. So we'd say that derivative, I wrote a second derivative there. First derivative does not exist at x equals 3. OK, so then the other part is thinking about where that first derivative is equal to 0. So I need to think about f prime of x equals 0. And find those critical values. All right, so I'm going to set this derivative equal to 0 and solve for x. So it looks very intimidating at the beginning. The algebra looks like it's going to be kind of horrendous. But actually, if you are smart and kind of take it one step at a time, it turns out not too bad at the end. All right, so one piece of advice in dealing with some messy algebra in this is to simplify those parts. So notice my original first derivative, I had kind of a mess here. But once I tidied that up, I'm a little more clear about what exactly that last part is. And that'll make your work easier. If you didn't already simplify it at this step in the problem. OK, so there's a couple ways I could proceed here algebraically. As long as you're doing things that preserve the equality and you're not changing the sides of the equation, there's a couple different ways through the algebra here. What I would do is anytime I have an equation that involves denominators, I like to clear the fractions. So I would multiply through by, let me see a different color here. I would multiply through by that denominator. So I'm going to multiply through by 2 times square root 3 minus x. And that will clear the denominators. I still will have radicals perhaps left in my problem, but that will clear the denominator. OK, so I need to remember to multiply both sides of the equation. But when I multiply all of that times 0, I will still just have 0. And then remember, my goal here was to clear the denominator. But I do get some nice simplification when I multiply this term that doesn't have a denominator by this 2 times square root of 3 minus x. The 2 times 2 will give me a 4. And then I have this x that's already there. And then I have the square root of 3 minus x times another square root of 3 minus x, which nicely simplifies. And we just get 3 minus x. And then this last term, when I multiply, this was my goal, was to clear the denominators from my expression here. When I multiply this, my denominator cancels with what I'm multiplying by. and I'm just left with minus x squared. And so kind of taking it one step at a time, dealing with one thing at a time, I was trying to get rid of that denominator, but in doing so, notice that the radicals also simplified as well. So sometimes that can happen unexpectedly in the middle of a problem, and that's a good thing. All right, so from here, it's not too bad. This is a quadratic equation. I've got x squared here, and notice when I multiply this out, I'll have an x squared here. So we've got a lot of tools for solving quadratic equations. Generally, you want that equal to 0, and then you can either use factoring or quadratic formula, depending on how the equation turns out. So I'm going to go ahead and distribute through and combine some like terms. So here I have 12x, and then here I will have a minus 4x squared and another minus x squared, so minus 5x squared. This one does factor nicely, so I'm going to go ahead and do that. I can factor an x out. And then we can set each factor equal to 0, and I get some other critical values here. So when I set this factor equal to 0, I'll get x equals 0. And then when I set this second factor equal to 0, 12 minus 5x equals 0. I'm going to skip that algebra here just to save space, but hopefully you're OK with that. I'll get x equals 12 fifths. 12 fifths does come out to be a nice decimal, so if you want to write that as a decimal, that's OK. I'm going to just leave it as a fraction. OK, so the values of x where the derivative does not exist or is 0 that are in the domain, all of these are in the domain. Oops, this one's not in the domain, right? 12 fifths, that is 12 fifths is 2.4, right? So that's not in the domain. So we're going to, oh, that is in the domain. Sorry, wrong side. 12 fifths. So that is in the domain. I was thinking about the wrong side of 3 here. All right, so you want to think about that. If that had been a value that was not in the domain, you would discard that. But 12 fifths is in this interval here, less than or equal to 3. So I have 3 critical values, x equals 3, x equals 0, and x equals 12 fifths. Those are all the places where the derivative is equal to 0 or does not exist. Those are all potential places for extreme values, maxima or minima, either local or relative or absolute extreme values. And in order to classify them and also find the places where the function is increasing and decreasing, this is where you want to make a sign chart. So our textbook shows this a little bit differently, but I usually make a number line. I put my critical values on that number line. And so this is a number line, so you want to put them in order and think about where they are in relation to each other on a number line. So x equals 0, and then x equals 3, and then x equals 12 fifths would be somewhere over here. You don't need to make that necessarily to scale, but you want to think about them in order from smallest to largest. Because I have a domain restriction on this problem, I'm going to also add some stuff here to my number line just to remind myself that this part over here we want to ignore. This part over here where we are right of x equals 3 is not even in the domain of the function, so I don't need to do anything with that. All right, so at this point, those critical values on my number line have split my number line, split the interval into pieces. So I have this part here that is left of 0. I have this part here that's between 0 and 12 fifths. And then I have this little part here that's between 12 fifths and 3. So I really have 3 different intervals that I've split my number line into. What I want to do is test the first derivative, test that first derivative and determine whether that first derivative is positive or negative on those intervals. That will tell me where my function's increasing or decreasing and whether these critical values are maxima, minima, or neither. All right, so remember that you're plugging those into that first derivative. You're looking for slope being positive or negative. So first derivative tells you about slope. All right, so sometimes students want to get out their calculator and pick a number in each interval to plug in. That's perfectly fine. You could pick a number left of x equals 0, say x equals -1, and plug it into that derivative and determine the sign on that. I tend to not pick a number, just kind of think about what would happen when I have a number that is less than 0, so that would be a negative number, and think about the signs on these. Sometimes when I'm doing that mentally, it can be a little bit easier to rewrite this with a common denominator. Notice that if you rewrite this with a common denominator, you get some of the same simplification that we got here. So I'm going to maybe go ahead and do that. If I do get a common denominator on this original first derivative here, it would be 2 square root of 3 minus x. And to do that, I would multiply this by 2 times square root 3 minus x and combine with that. So my numerator would be this 12x minus 5x squared, or in factored form, x times 12 minus 5x. There's the simplified, completely simplified form of my first derivative. So I'm going to actually just use that to think about positives and negatives. When I plug in a number left of 0, like -1, this x will be negative. This 12 minus 5x will be positive, because I'll be plugging in a negative value here. That'll be positive. This expression on the denominator will be positive. If I plug a negative number in here, that'll be positive. So I'll have a negative times positive over positive. That'll make that whole expression negative. So my first derivative will be negative in that interval. That tells me that my function is decreasing in that interval. Between 0 and 12/5, say at x equals 1 or something like that, we want to think about the signs here. So at x equals 1, I'll have a positive, and a positive. So everything there will be positive. That first derivative is positive. Tells you the function is increasing on that interval. So that tells us a little bit about what type of critical point this is here at x equals 0. And then between 12/5 and 3, I need to think about all those signs. So that's just a little bit left of x equals 3, thinking about the signs on all of these. So a little bit left of x equals 3, x will be positive. 12 minus 5x, however, will be negative. So if we're just a little bit left of x equals 3, this part will be negative. So positive times negative. This expression down here will be positive. Positive times negative over positive is negative. So our first derivative goes positive, negative, positive. And then our function is decreasing, increasing, decreasing. All right, so that tells us, and we should, this is kind of the work to justify it, but we should write down actually the intervals on which the function, it is decreasing on these two intervals here. So this interval left of 0 would be negative infinity to 0. And then this interval between 12/5 and 3, I'm going to close that boundary at 3 since that's the edge of our domain. The function stops there. If I had more and it switched to increasing in that next interval, I might use that as an open interval. And then our function is increasing on this interval between 0 and 12/5. Notice that at 12/5 and at 0, it's switching from increasing to decreasing, or vice versa, so I didn't include those in either of those intervals. This sign chart also tells us whether we have extrema at those values. So this tells us that we have at least a local minimum. Maybe it's an absolute minimum as well at x equals 0. So I'll write that here. So local minimum at x equals 0. The actual minimum value of the function would be the y value of the function at x equals 0, which we happen to have already found from our work over here. That happened to be one of our x-intercepts. So at x equals 0, we've got y equals 0. So the local minimum is y equals 0, and it occurs at x equals 0. I also have a local maximum at x equals 12/5. And the actual local maximum value would be the y value of the function at that x value. So I don't already have that here in my work. I'll need to plug that in to the original function. So when I plug 12/5 into the original function, I'm not going to worry too much about simplifying this, but 12/5 into the original function, I square that out front. I'll have y equals 144 over 25. And then inside the radical, I'll have square root of 3 minus 12/5. I might go ahead and simplify that. 3 is 15/5 minus 12/5, so square root of 3/5 inside the radical. You could simplify that a little bit, but that's the local maximum value. And then over here, I will have another minimum value. That's an end point of the interval, but I'll also have a local minimum value at x equals 3. That's a low point on that region of the graph. And that also is one where I happen to already have my y value here. That happens to be an x-intercept, so we know that the y coordinate is 0 at that point. Okay, so that means that what I expect my graph to look like, we'll look at it on the computer in a second here, but what I expect my graph to look like roughly from this work here, I've got these two as local minimum values, so the function shouldn't go below that. I have at x equals 12/5 a y coordinate, so I'm just going to kind of estimate where that's at. It's going to be up here somewhere. And I should expect to see my function kind of as I go from left to right being decreasing, then increasing until I get to there, and then decreasing again. So we'll look at it on the computer and make sure that we see what we expect to see. That might alert you to any errors that you have in your work here. And also get a little bit better picture of where exactly I want to plot this point if I'm going to sketch the graph. So I did a rough sketch just based on my work here, and now I'm going to check that with a graphing calculator or computer. I'm going to go over to the computer and look at that. So here you can see that I've graphed the function y equals x squared times the square root of 3 minus x. When you graph that, remember you probably need on your graphing calculator parentheses around the 3 minus x that you see there. I've also plotted a couple points here, one of them at 3, 0. That's our end point of that function, and a local minimum, another at 0, 0. And then you can see here I plotted that point 12/5 comma 144 over 25 times square root of 3/5. I'm on Desmos here. If I click label, it'll show me a decimal approximation for that point. So that's approximately where we expect our maximum value of the function to be. And you can see that the end behavior that we came up with agrees with the graph here as well. All right, in another video, we're going to look at second derivative information for this same function. So we'll just add a little bit to this graph in the next video.